Okay, so we are now in the chapter 12, section 1, dealing with Anova. Anova is one-way analysis of variance. It's a statistical technique that's used to test a hypothesis concerning the comparisons of three or more means. So typically we use the f-test from an f distribution to test our claim. So let's look at a claim. Let's say, suppose a researcher wishes to see whether there is any difference in the weight gains of athletes following one of three special diets. Athletes are randomly assigned to three groups. These are also known as categories, and placed on the diet for 6 weeks. The weight gain in pounds are shown here. At alpha 0.05, can the researcher conclude that there is a difference in diets? We should say that there is an average difference in diet. So we have the paleo diet, nut fruit diet, and the meat diet. These are the weight gains for the athletes. Step 1, we need to compute the mean and variance of each category. So we calculate, we can use our calculators to accomplish this. So the mean and variance for the paleo diet is listed here. Also, I list the sample sizes. Those values will also be important. For the nut and fruit diet, we have our mean, variance, and standard deviation. And for the meat diet, same thing here. Next, we state the hypothesis and identify the claim. So the structure of the hypotheses are the following. H naught will have all the means equal to one another. So in this case, we have three categories. That means we have three means that are all equal. H sub 1 is at least one mean is different from the others. That's also the claim. So there was the claim was difference. So at least one is different. Step 3, we have to find the critical value. So remember, K is the number of categories. There's 3 categories. N is a total number of data points. So you just count up all your data points. I believe there's 14. So the degrees of freedom of the numerator is K minus 1. So K is 3 because we have 3 categories, so 3 minus 1 is 2. The degrees of freedom of the numerator, that's N minus K, so N is the number of values, 14 minus the number of categories, 3, so 14 minus 3 is 11. And as we mentioned above, alpha is 0.05. So at this stage, we turn to table H. So table H, if we take a look at our tables, we go down to table H. Table H. And we have to, when we arrive at table H, each page is a different alpha. So we have to search for the alpha that's been given to us, which is 0.05. So there's our alpha, 0.05. Remember, degrees of freedom of the numerator, 2. Degrees of freedom of the denominator, that was 11. So 3.98. That's the critical value. It's right here. 3.98. There's another way of examining how to find it. Next step, we compute what's called the grand mean. So the grand mean is basically the mean of all your data values. So these are all the data values here. You just add them all up, divide by 14. So in this problem, the grand mean is 99 divided by 14. We round it to 7.07. Step 5, we find the between group variance, which is finding the variance of all the means. So to accomplish this, we have this formula here. It's between group variance, it's the sum of each sample size times the difference of each mean with the grand mean squared all over the number of categories minus 1. So remember, for the first data set, sample size was 4, mean was 5, subtracted from the grand mean squared. Second data value, so we're going to add that. So the sum tells us to add that product with the product of the second data set. N was 6, mean was 10.7 minus 7.07 squared. And finally, with the third data set, that should be 4. All right, so it's going to be 4 right here. There's 4 data values. Times the mean, 4.5, and so on. So we end up, as we do our calculations, it's 101.22 divided by 2, which gives us 50.61. So that's our between group variance. We also compute the within group variance, which is the variance of all the data values that is not affected by the differences in the mean. So this is our formula for the within group variance. In the numerator, we find the sum of each sample size minus 1 times the variance divided by the sum of each sample size minus 1. And if the between group variance, which we calculated here, is close to the within group variance, then there's no difference between the means. In that case, the test point will be close to 1. But let's calculate the numerator and denominator. So I use different colors to compute the numerator and denominator. So for our first data set, we have 4 minus 1 times the first variance, 3.33, plus, that's what the sigma tells us to do, 6 minus 1 for the second sample size times the corresponding variance, plus 4 minus 1 times 7, which was the third variance. Let's double check that. Yes, it's 7. So perform our calculations, multiply, and then add. So in our numerator, it's 71.84. Our denominator, we just take each sample size minus 1 and add them together. So 3 plus 5 plus 3 is 11. Divide, we get 6.53. Now finally, we calculate our test point. Remember, we're using the F-test. So F is the between group variance over the within group variance. So we divide 50.61 by 6.53. We get 7.75. Now we make our decision. So we're using the F distribution. It's asymmetrical. All the values are positive. It's a right-tailed test. We saw that the critical value is 3.98. 7.75 falls in the critical region. So we reject H naught. We say there's enough evidence to support the claim. And so that is an example of performing Anova, one-way analysis of variance.